Okay, let's begin. So later today, we will start talking about project number 1. It is due on Monday, October 14th at class time. Last time, you hopefully remember me mentioning this group sign-up sheet here. What I'm going to do is pass this around the class. And please sign your name in one of the 4 options shown there. If you're doing option 1 or option 2, please make sure you draw like a circle around all the names of the people who are in your group. If you're not 100% sure who is in your group at this time, you can still sign the sheet if you want to at the end of class. Just don't leave here without signing the sheet. Okay? Any questions about that? So today we will continue with the graphics section. We will talk about project number 1. And I think I was a little overly optimistic, and I have principal component analysis listed there, but I don't think we will get to those notes today. Do note that, as you probably saw from the listserv post, the actually departmental website is down, so you can't actually get to my course website, unfortunately. Sometimes I wonder how long it will take for someone to notice this, but I won't play the waiting game, and I will talk to our computer support person after our class. It works? Are you sure it's not cached? Maybe it might be stored on your computer, and the computer's just bringing up a previous version, because I cannot go to any of my websites at all. Well, although I doubt it, maybe it's an Internet Explorer problem.
I was on it this morning.
Well, that's odd.
I can't get on it. I didn't work or on
What browser were you using?
Firefox.
Okay. Now this is Chrome, and I have no problems. Well, this is very odd. Because if it works in one browser, it should work in all the browsers. What's that? Yeah. Well, at least for now, I recommend using a different browser if it's not working in the browser that you're using. Sorry about that. Like once, I think it was last year, I was teaching a course in this room, Stat 870, and I was having some students from SRAM say to me that they could not access any of my websites at all from where they have, from their SRAM location, which is a building downtown. Never could figure out why that particular location they couldn't access any of my websites. The only thing I can think of is if you ever do a search for Builder, like a Google search for Builder, what will often pop up is the German meaning of Builder, which means picture, and often this is associated with German porn websites. And so maybe you know, certain computers are blocking Builder from any kind of from being able to access it. Anyway, enough about that. Let's see now.
So, where is the SIM data set? I can get in now.
Okay. It should be, you know, unless I unfortunately accidentally did not put it out there. Let's see. So that would be, yeah, so it would be for the graphics section. Looks like I had not put it out there. So I will put it out there. Sorry about that. Unfortunately, I wasn't able to check last night because I was using Internet Explorer. Unfortunately, little problems like that will pop up since, again, I'm rewriting all my lecture notes, and that will happen. That I will forget to put files out there. Okay, any other questions before we get going? Let's see here. So we were on about page 30 of the notes. talking about this example from a paper that I wrote involving Monte Carlo simulation. Often people forget to realize that when one is actually doing a Monte Carlo simulation study, that the result that they get back is essentially you can treat it as a data set and analyze it through using multivariate methods. And so essentially that's what I did here with respect to using parallel coordinate plots. And just to recap, what I was doing was I was investigating 4 different ways to estimate a particular type of regression model. The exact type is not of interest here, rather what's of interest is how I summarize the corresponding results. And so these 4 different methods are called individual, alike, random, and different. And I have about 500 different I have 100 simulated data sets. And for each of them, I estimate like a slope coefficient. Let's call it beta hat 1. Ideally, I would like for all these methods to have exactly the same beta hat 1. Because if they have exactly the same, it says all 4 methods are performing exactly the same. If they are different, then that's where I can start making a judgment of, well, maybe one method is better than the other. And indeed, that's what happens here. And so this is the parallel coordinate plot, if we just look on the right-hand side here, that was produced. Note that the color in the plot is not really important here. I just try to use different colors for each of the lines to some respect. Obviously, I don't have, it's hard to use different colors for every single thing. But I try to use different colors here just so that you can better see the lines. The thick red line that's shown to have a label of beta 1, that's the true value of beta 1 in this simulation study. So I know what the true value of beta 1 is. And so I just draw a simple line across my plot at where beta 1 would be. Now we see a few things from this plot. First of all, this is not the normal kind of parallel coordinates plot that we talked about last time. Rather, what I did here was I fixed the y-axis in this plot so that it was same for each of the variables. If you remember with the parallel coordinates plot, what you typically do is you have the lowest value for a particular variable at the very bottom, the highest value at the top. Instead, what I did was I fixed the y-axis for each of the variables so it actually has a numerical scale to it. And the reason why I can do that is because each of these 4 variables are methods that are estimating exactly the same thing. So they're on the same scale already. Okay? And so, what can we see in this plot? What immediately jumps out at you? Which one has the least variability of these methods? The individual, yeah. And the like is not too much larger. So, often in statistics, we're very interested in minimizing variability. So if I want to minimize the variability of a particular statistical method, I would prefer individual or like versus random or different. What else do you see from this plot?
Looks like in terms of relative to the true value, if random is high, different is to be low, or vice versa.
Yeah, to some respect. I mean, one thing that you could do is maybe cheat a little bit and take a look at the box plots that I have over here. I know I didn't mention them, but obviously, of course, this line in a box plot is the median, and we can see that for the first 3 methods, roughly, the true value of beta 1 is kind of right in the middle of all the beta hat 1s that I get, which is what you would hope typically for a statistical procedure. That if you repeat it over and over again, you would expect on average to get the true value. Remember ever hearing about unbiased estimators, for example, in another class. But we see the different there might be a little bit biased. It's starting to get a little bit lower values, more lower values than what we would necessarily expect if this was an unbiased method. There's one other thing that I see in this plot. Do any of you see it? It's a very important thing. Remember, ideally, I would like these statistical methods to produce the same beta hat 1s, okay? Is that happening? No. Look at random compared to different. The highest beta hat 1 for random, look where that goes. The lowest value for different. And in fact, the lowest value for random, well, it's almost about the highest, if you follow the line up, almost about the highest for different. So I am not getting this consistent behavior that ideally I would like. Am I getting that for individual versus alike? Does it seem like things are being consistent? Roughly. It's not perfect. But it's a lot better comparing random to different. And even if you compare alike to random, you see that, if I have a large alike value, notice how that translates into a large random value as well, generally speaking. It's not perfect. But again, when you compare random to different or even different to alike, you see some problems. So from this little simulation study, what this allows me to conclude is that this alike method is very similar to individual. I'd be very concerned about using the different method for estimation. So I'm going to get some odd results in comparison to if I use some other method. So it's a very, very useful plot to help summarize what was going on in this Monte Carlo simulation. Any questions? Okay. Now, one of the reasons why I bring this plot up, or I bring this particular plot up, is that, if I use the par chord function that we talked about last time, I couldn't get this exact plot. Instead, what I had to do was modify the function for my own needs. And that's one of the beautiful aspects of R, is because nothing's hidden to you. You can actually see the function code. You can see how the function actually works by simply looking at it. So if I type par chord, there's the actual function. Okay. Now, especially if you're a beginning user of R, when you look at the function code, it can be kind of complicated. So how do you learn what each of the lines does? Well, what you can do is this. Copy and paste the code into a program editor. That's what I've already done here. Oops. So I copy and paste the code in there. And what I'm going to do is step through each line of the code, one at a time, and see what it does. And that's how you learn what R is doing. And so to do this, then, I need to first of all set, well, what would be X? What would be my color? What would be my line types? What would be var.label? So what I did was, for demonstration purposes here, how about we let X be the serial, for the serial data set. So if you remember from last time, oops, sorry. So if you remember from last time, when we used the serial data with the par chord function, we set X equal to the first column and columns 8 through 10 of the serial data set. I set some colors up. I also put a title on my plot as well. And so I'm going to let COL for color be my shelf color. I've already created the shelf colors from last time. I'm going to create a main title for my plot. Notice you do not see main as one of these arguments here. How does anyone know how R knows that this is then corresponding to the plot title? This is a little bit more of an advanced part of our program. See this ... What this allows you to do is pass in additional arguments that maybe functions inside the function, the main function, will actually be using. And so I'm going to pass in this additional argument, main, and in fact it's going to correspond to, which one is it? Well, I don't see it off the top of my head. I thought it was matplot. I'll have to look into that a little bit more. But anyway, as you will see, a plot title is put on the plot. var.label equal false. This is just a default value. I'm just going to stick with it since I never set it to begin with. And so I'm just going to highlight this set of code. And also we'll do the same. We'll keep the line type at 1. Okay. Now what I can do, now that I have these argument values, I can step through each line of code one by one. So to see what this first line does, I just highlight it, run it, type the Rx as a result. And what we see here is that we have basically a range. Well, that kind of makes sense. If you notice, we have the word range inside of there. And we have a range basically for each of the variables that were in my data set. Let's look at the next line of code. What's in X? Well, X actually contains my adjusted data. Remember, on a parallel coordinates plot, typically always, the bottom value is going to be the minimum for a particular variable. The top value is going to be the max. And so to get that to happen across all your variables, you need to do this little transformation here. Take each variable, subtract off the minimum, divide by the max minus the min. And that's what this apply function essentially does. It applies this little transformation to every column of your data set. Okay. Now let's look at what matplot does. Mat stands for matrix, plot stands for plot. And so now things are starting to look a little bit more familiar. We have now my lines on my parallel coordinates plot. Axis, that was a function that was looked at in the introduction to R notes. This allows me to put some stuff on my axes. I'll look at that. Now I have names on my bottom of my x-axis. And then I have a little for loop, which essentially puts the vertical lines that you see here on the plot. And so now I have an idea of what this function does, and now I can modify it for my own needs. So in particular, this is the function I ended up using on page 33. I'll let you play around with it on your own. The main thing is to notice that I don't have some of those two lines that we saw at the very beginning of the function to begin with that transform the data. Instead, I want to print, basically use the raw data itself. So when I use X here, notice what's happening here for this matplot is going to plot then the actual data that I pass in. It's not going to transform it at all like what we had seen through these two lines of code. Okay? And that's how I got this particular plot. Now, obviously, I have not went through all the details of doing this. And what you will see in the homework is that there's an opportunity, because you're going to be doing some stuff with a simulation study, some stuff that I did with a simulation study for another class. You're going to have an opportunity to do some plots. And this particular function can come in kind of handy. Okay? And we'll give you some experience with it.
What does 2L mean in apply?
Yeah, basically what that means, you know, I haven't been able to find too much documentation on it, but it's the number 2. Yeah, I know, it is odd. And unfortunately, I have not been able to find documentation why they use that.
The apply function can either tell it to work on rows or columns. 2 tell it to work on columns, but
yeah, 2 would tell it to work on columns, but I don't know why 2L. And I rarely see that used, but I've seen it used in some other places. I've tried to look it up in the various sources, say why it uses that, and I haven't been able to figure it out. You know, in the end, you know, there are, you know, this happens whenever you're using a computer language, that you might not know why something's used, but you can usually figure out what it does. And that was the purpose of this little demonstration. You saw what it does.
We have a question. The original R code function,
Yes.
where does it actually use the Rx that it makes?
The Rx,
Because in the function it uses max and min functions.
Oh, yeah, that's a good question. I don't know.
It's down in the text.
It is? Okay, so it is being used down there. I haven't looked in specifically how that's used with respect to labels. So,
Maybe it labels the axis to say what the min and max values are. I guess that's
well, yeah, it doesn't. So,
well, yeah, you have more of it, which is always dependent on it. They label the axis with min and max values.
this is then a great tool where you can just delete this and see what it does, and that's how again you learn what this kind of code does. Okay. So page 33. Also something I think is very important to understand whenever you're doing plotting. Often it's hard to get the plot maybe perhaps exactly the way that you want it. And that's what happened in this particular case when I was trying to get this paper ready for publication. So what you can do in these instances, if you've never thought of this before, is simply, let's say, copy this plot and bring it into some kind of graphic software package. I'm just going to simply use PowerPoint here. Put the plot in there. And now let's say that I wanted to add some stuff to the plot, such as, let's see here. What would be something good? Maybe I want to come up with some kind of unique title. So, unique title. And, I could put that there, or I could, twist it whatever way that I want it, or I can do a variety of other things too. So, for example, like that beta 1 that you saw listed on page 31, that red line, I essentially put that in there in PowerPoint. Okay. Now, let's say that you're doing just for demonstration purposes. Let's say you're writing your paper in Word. Well, then what you can do is just simply copy this annotated plot into Word by simply going to the slide, copy it, just bring up a new window, and then paste it in there. Okay. So don't get try not to get frustrated that you're trying to do some small little thing about the plot in R or even some other software packages. And use it for other software packages too, where you're trying to do something you just can't get it right. Well, if it's something that you could just simply like add text to or maybe add a line to, just bring it into some kind of graphic software package where you can edit it, add annotations, do what you need to do it, and then save it out as a file or bring it directly into Word. So a nice, useful tip. Okay, so page 33. We're going to talk about another plot type called trellis. These were developed at what was then called AT&T Bell Labs in the early 1990s. They're a really, really cool plot. I still remember the first time I ever saw these plots. It was a stat PhD student in my department at K-State. He was doing his dissertation defense. This was spring 1995. And he had developed a new statistic. And he decided to call this statistic G. So, again, the guy's name is Eric Gibson. He decided to call this statistic G. And he was using this trellis plot. He was using some trellis plots to summarize some Monte Carlo simulation results that he had that showed his statistic was best of all the rest. Now, it is kind of a faux pas to name a statistic after yourself. Okay, and Dr. Dallas Johnson, again, you saw his picture last time. He at the end of Eric's seminar immediately raises his hand and says, "Did you name that statistic after yourself?" Eric looked at Dallas and said, "No, I decided to use the letter G because the statistic was good." And that took care of that. Anyway, perhaps you have to think of it in the context of you got this professor that maybe you might be scared of, and you're telling that to your professor. Okay, so what is a trellis plot? Sometimes these are also called co-plots, where co stands for conditioning. Because the way, and what we've been doing is trying to get as much variables on a plot as possible. The way that you can get additional variables on a plot, in this particular case, is to condition on particular variable values. So for example, let's say you have 3 variables, x, y, and z. Maybe you want to do a scatter plot of x and y, and what you can do is do a few different scatter plots of x and y, conditioning on maybe a range or particular values of z. So you have one plot that has, let's say, z between 0 and 1. Another plot for x and y of z between z for 1 to 2, and so on. And so these plots then are arranged in a trellis-like structure. Okay, so you can imagine, let's say, all these little squares in here could contain a particular plot. And again, each of these plots represent, let's say, a slice of your data that comes about through conditioning on a set of variables. Here's one of the most famous trellis plots ever constructed. It's famous because this was a data set in Sir Ronald Fisher's famous experimental design book. If you do not know who Ron Fisher is, he's one of the basically early founders, you could say, of the statistical science, and a lot of stuff that he did back in the early 1900s we still do here today. And so he wrote this famous book in the 1930s that went through a number of editions, and in the book he analyzed this particular data set. And what we have here graphed is a trellis plot of the data. On the y-axis you have different different barley varieties. So you can see we have about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different barley varieties. On the x-axis you have barley yield, and basically what we have is yield for 1931 and 1932 at 6 different locations in Minnesota. So what we're doing is we're going to condition on location to illustrate what the barley yield was. So for example, at the location of Grand Rapids, we see that the barley yield for the treble variety was about 21 in 1932, and in 1931 the barley variety yield, or the treble yield, was about 31, 32. Okay, so that's how you can read this kind of a plot. Very simple plot in the end. But what do you see here? Well, you see, typically the blue points for 1932 are less than the pink points for 1931. At every single location in Minnesota again, except for one location, up at Morris. Notice the reverse is true. No one really had paid attention to this until they saw this with a trellis plot. No one had ever brought this up. Again, this was in the 1930s this data set was analyzed, at least first time in a book, and trellis plots didn't come about until the 1990s. And so when some researchers saw that, they went to do some investigating to see, well, could this really happen? Did this really happen, or was it maybe a data entry error? And indeed, they found out it was a data entry error. So people have been analyzing this data set for 60 years to demonstrate various things, and here there was a data entry error in it. So anyway, it was an interesting result. In R, there are 2 main ways to do trellis plots in terms of packages. There's a lattice package, and there's a ggplot2 package. We're just going to talk about the lattice package here. The reason being is because the code associated with it is a lot more similar to the kinds of plotting code that we've looked at already in comparison to this ggplot2, which looks at graphics in a different way. I'll talk a little bit more about the ggplot2 package later, though, at the end of these notes. So what you'll notice is that sometimes when you want to get the plot a certain way, it does take some extra coding to do this. So again, think of my code as a template, or at least an idea of how to do stuff so that you can find maybe another function to produce the plot that you truly want. Okay, so let's look at the Trellis plots or Trellis graphics in the context of the serial data set. So we're going to do just a few plots with it to demonstrate how to use this plotting idea. Now, in order to do these plots, we need to transform the structure of our data. We need to go from what's a wide format to a long format. Let me demonstrate what I mean by that. Currently, our data is in a long format. And let's just look at columns 1 and 8 through 10. It's called a wide format because notice that each variable is a separate column of our data frame. So you're kind of wide. Instead, what we want is what's called a long format, where essentially what we want to do is still have ID here, but maybe create a new variable. Suppose we call it amount, let's say. And for the first 40 rows, we put all the sugar values in there. And then right underneath these 40 rows, it has the ID and the sugar amount. We put in the ID variable again and all the fat. All the fats go into the amount column. Then we do the same thing for sodium, so that in the end, instead of having 40 rows for our data set, we have 120 rows in our data set. That's called a long format. And we'll add another variable to the data set. Wow, this particular row is sleeping a lot here. I don't know if there's something about this particular place in the classroom, but it must be kind of tiring. Anyway, we're going to have another column in our data frame that says, okay, was this particular row value a sugar, fat, or sodium value? Okay, so it's another kind of identification value. To help demonstrate the idea, let's take a look at, or how to do it. Let's take a look at a simple data frame. And what I have here is a data frame. This is on page 37. I have a data frame I just simply called set1. It has simply 3 rows to it. If you're familiar with longitudinal data, this is essentially a longitudinal data set where we're going to make some observations over time. So what we have here is maybe the person's name in a particular study. We have corresponding identification number associated with that person. We have some additional information describing the person, their age. And then we also have, at time 1, what was their response? Was it a 1 or a 0? I just decided to make it binary in this case. And then at time 2, what was their response? Then I would like you to add also to your data frame that you see in the notes this time var called time. So another column called time var, and then just put the word time in. It's not needed. All this stuff is going to work if we don't have it. It's just a little bit of a useful tool in this particular case. So notice what I did here in my data frame. Okay. So now what I would like to do is transform it similar to how I described with the serial data set, where basically what I want to do is instead of having 3 rows, I want to have 6 rows to the data set, where I have one overall column that corresponds to the actual response that I get at time 1 and also time 2. So to do this, I use I'm going to transform it to the long format. I'm going to transform it using the reshape function. So I say reshape data equals set1. The variable that's going to identify each, let's say, individual in my study is going to be called id.name in terms of what came from up here. I could have also used the id.number. I just decided I essentially have two ways to identify every individual. I just chose one. Then the variant argument says, okay, what columns of my variables do I want to transform to be just one variable overall? Well, it's time 1 and time 2. Then, well, what name do I want to give this new column of information or data? How about we call it my response? The direction of reshaping, the long format. And then I don't need this extra identification variable, so I'm going to just drop it out of my data frame. And so let's run this code. Oops, didn't mean to do that. And now here is my long format. So you see response. It has all the 0, 1 responses. We have a variable called time that tells me, was this the response at time 1 or time 2? Okay. We have also then id.name here. Notice here's subject 1. Here's subject 1. Okay. Now notice we have also over here something subject 1.1, subject 2.1, and notice it doesn't have a variable name to it. In terms of it doesn't have a column name to it. And so you might be thinking, okay, well, how can I have a variable in my data frame that doesn't have a name to it? Well, actually, it's not an actual variable. Similar to how each column can have a name, well, each row can have a name, and by default, using this function, this reshape function, it actually gives it gives row names to each row of your data frame. To remove that, because we don't really need it, you can use a row.names function, set equal to null, which says don't have any row names. And let's take a look at the result. And there you go. If you want to, you can transform the data set from the long format back to the wide format. I'll let you look at that on your own. There's the corresponding code. Okay. So the whole purpose of that small little data set was to help us ease into how I'm going to do this with the serial data set. So the serial data is in the wide format. I need to transform it to the long format so I can do some Charles plots. So I'm going to create a data frame called serial.long. I'm going to reshape it based upon the original serial data frame. My ID variable is going to be the ID variable in the original data set. I'm going to drop a whole bunch of columns. Which columns do I want to be just one column overall? Sugar, fat, and sodium. The time var is going to be content. This is going to tell me is this going to correspond to sugar, fat, or sodium in a particular row. V.names amount. That's going to be the column name for the column that has all the sugar, fat, and sodium values. And I guess let's see now. Sorry. Off the top of my head, I don't remember why I have the. Okay. Yeah. The times argument is going to correspond to the names sugar or the sugar, fat, and sodium. You'll see this its effect when we do it, and direction equal long. Okay. Let's do this. Okay. So look what we got here. The ID variable. This is the first 6 observations. Happens to be shelf 1. There's a serial name. What is in the amount column? Well, in this case, sugar. The tail, or the last 6 observations of the data set, structured the same way. Notice it's shelf 4. Now I'm dealing with sodium. Let's take a look at rows 39 and 40 in the data set. I'm sorry, 40 and 41. So remember, there's 40 observations originally in the data set. So this is where we would expect some differences in terms of the content. Glass sugar, the first fact. Okay? Notice how the shelves change as well. Are there any questions about that? Unfortunately, the description that I gave you was not as good as I had intended. Let's see here. This right here on page 39, I show you how you can do basically the same thing with the standardized data. So if you remember, we had created a object called, excuse me, we can create the standardized data using the scale function. Well, if you notice the part that I've highlighted, or that if you look in your notes, the part that's up here is exactly the same as up here as down there. That is a typo. Instead, just run it on your own, run the code on your own, and you'll get the data that looks like this. Okay? It's not that big of a deal. It's just like copying and pasting stuff incorrectly. Okay, so now let's do some plots here. Let's do some histograms. So I'm going to use the Lattice package. This is automatically installed in R, so you don't need to download it. But you do need to say library Lattice to tell R you want to use it. And then I'm going to create a histogram. What I want a histogram of, what I want to summarize is the stuff that's in the amount column. And I'm actually going to just work with the standardized data here. So all the standardized amounts. But I want to condition on, and how you tell what you're conditioning on, use that vertical line there. I'm going to condition on the content variable, which tells me if it's fat, sodium, or sugar, and also the shelf variable, which tells me if it's shelf 1, 2, 3, 4. I specify where my data is located, Z serial long. The type of histogram that I want the percent of observations that fall in each histogram class. So I'm going to put percent. Layout, that controls how many rows, how many columns you're going to have in the plot. Now this is something that's kind of odd. The first value here corresponds to the number of columns. The second value corresponds to the number of rows. I don't know why the syntax is like this in Lattice, but that's just the way it is. I put an x-axis label, main axis title to it, and here is my trellis plot. So you can see I have 12 different histograms corresponding to the shelf, and also if it was fat, sodium, or sugar. Now, remember, we only have 10 observations per shelf. So, this isn't necessarily the best graph to do, since each of these histograms just represent 10 observations. But you can imagine other settings where you would have more observations, and that this might be helpful. But we can see a few things in this plot. First of all, let me make sure you understand this aspect here. Notice how R is denoting the shelf number. It's putting this little darker line in each of the parts there. This is because shelf is a numerical quantity, 1, 2, 3, or 4. And so when you're at the left side, that's 1. When you're at the far right side, it's a 4. So this is shelf 4 up here. This is shelf 1 down here. We'll look at how we can change that later. Now, some terminology too. Each of these little plots here in a trellis plot is called a panel. That is in my notes. It's earlier. I just forgot to say it. So each of those little squares, you could say, or rectangles, is a panel in a trellis plot. And so by taking a look at this plot, what can you see? Think back to what we've seen before with with plotting the serial data. What stands out? the shelf number 2, all the sugars are on the high end. And now take a look at this. There's where 0 is. We have standardized data, so we can see that for shelf 2, all the sugars are kind of big. Remember how we saw that before with some other plots, that for shelf 2, we seem to have higher sugar content cereals. Also, take a look at that. There's something that we maybe haven't talked about before. Shelf 1 and sodium. We have a similar thing happening. And so you can see with these trellis plots, and we saw this with that barley yield data, how you organize where the panels are located can help you compare from one panel to the next. And so we see for the sugar content here, for example, shelf 2 tends to have higher sugar content cereals in comparison to the other shelves. Similar thing happens with sodium in shelf 1. Okay, any questions? Okay, well, again, the reason why we had these little lines here was because shelf is a numerical variable. And so, when I did this plot, I didn't really like having just the lines there. I like to know what shelf number is it. If you wanted to, you could actually copy and paste this this plot into PowerPoint, for example, and actually type in text box shelf 1, shelf 2, shelf 3, and shelf 4, and actually arrange it like that. Alternatively, it's not too hard to get the shelf numbers to actually appear in R. So what I'm going to do is create a new data frame. Oh, let's actually go ahead and do it. I'm going to create a new data frame that, here we go, based upon this Z serial long, which has the standardized data in long format. And I'm going to put a new variable in it called shelf.char, for character, essentially, where I'm going to transform those numbers to characters, at least the way that R recognizes it. The way that you can do that in R is use a function called factor. So let's just take a look at what the shelf looks like without using factor, just to verify that. So that's numerical. And then if I do it with factor, notice it looks exactly the same except for you see this right here. That's the way R designates, okay, this is actually a character variable. You have a finite set of levels to this character variable, 1, 2, 3, and 4. And so I put that then all together into a data frame, into z.serial.long2. It's kind of a big data frame. This is what it looks like. Alternatively, what I could have done too, we've actually used this kind of syntax before, if I wanted to just to keep the original data frame itself, I could have done this. Where I immediately create a new variable called shelf.char and put the factor results in there. I could have done that. Those would have been equivalent. I just, for some reason, just chose not to. Okay. So now I'm going to do the histogram again. Exactly the same as before, except for now I have a different variable there, and I have a different data frame name there. And here we go. And there's my plot. Now you might be wondering, okay, well that's great that we have the shelf numbers there, but it would be nice if I actually knew that those numbers meant shelves. Well, how do you do that? That's not too difficult. In the exact same code that we had before, what I can do is actually always put with each of those numbers the actual word shelf. So the best way to do that is if I come over here, I can use a function on R called paste. I'm going to paste the the character string shelf equal with the shelf number. So if I just run that segment of code, you can see how everything's pasted together. And when I combine that with the factor, now you can see how R is treating it. And let's go ahead and run the corresponding code now. And now we have a plot that looks a lot better. Are there any questions? Okay, let's keep on going here. Page 43. Now, often, whenever you see a plot like this, whenever you have a histogram, what you might want to do is like kind of superimpose maybe a normal distribution curve on it, or maybe something that's a little bit more flexible in terms of to approximate what the density looks like. You can do this in a trails plotting situation as well. But the issue then is that the code, unfortunately, becomes a little bit more complicated. I'm going to briefly talk about that here. What I'm going to do is add what's called a kernel density estimate to each of those histograms. So I'm going to essentially do 12 different kernel density estimates. If you're not familiar with what a kernel density estimate is, don't worry about it. The main idea is that I want to basically superimpose a line like that on top of the plot. We actually saw that a little bit earlier in the course. We were talking about multivariate normals and superimposing some kind of density estimate on top of one of those plots. And so what I can do is use exactly the same code as earlier, except I add a new argument called panel. And what this allows you to do is have a great amount of flexibility about what is going to be in each of these panels. Well, what do I want in each of these panels? I'm going to put a histogram, and I'm going to put a density plot. And so if you look at the corresponding syntax for those particular functions, they're in the help for lattice. You can get an idea of what those functions do. Basically, we see here this x. Well, the x that's passed into here, or the x goes basically into there. And essentially what you're doing is writing your own little function inside another function to do this. Okay. What about scatter plots? You can do scatter plots as well. So to do a scatter plot, use a function called xy plot. And let's say I just simply want sugar on the y-axis, fat on the x-axis, and I want to condition on shelf. So notice here's a little bit of a different way that I can get shelf equal like 1 or shelf equal 2 on the plot, where instead of just putting a variable that says shelf, I actually use that factor paste stuff that we saw before, and I put it right inside this function code. And there's my 4 different scatter plots for each shelf. Page 45 shows how to do one of these plots too, where maybe instead you would like to put some grid lines on your plot. Maybe you would like to put a simple linear regression model on your plot. And the way I had to do that, or the way I did that, was to use then this panel argument, where inside this I wrote a function, and I make a call out to panel.xy plot. Panel.grid puts the actual grid lines, and panel.lm line, linear model line. And that's how I can get that particular plot. If I want to do some 3D plots as well, I could do that by using the cloud function. On my y-axis, I'm sorry, that's actually going to be my z-axis, I'm going to put sugar. And then I have fat and sodium on my x and y axes. And here is a 3-dimensional plot. Fortunately, you cannot rotate. That will be kind of cool if you could rotate, let's say, all the different plots in each panel at the same time, but you can't do that. And that takes us then to page 46. Okay. I want to at least briefly stop there so we can talk about the project. So let's talk about the project. If you have a copy of it, please take it out. Okay, so again, as I've mentioned before, you can work in groups of up to 3 people. The project is due at class time, so that's 9 a.m. on Monday, October 14th. When you complete your project, email it to me. So obviously that means you're not turning in anything on paper. What you do turn in to me needs to be in a Word document so that I can easily grade it using my tablet PC. After I receive an email from you that contains the project, I will send you an email back to confirm that yes, indeed, I received it. If you do not receive a confirmation from me, that means I did not receive it. And so you need to contact me to figure out what's going on. Okay. So here's the project. It's based upon one data set. And it's based upon an example that's in chapters 2 and 5 of Dallas Johnson's 1988 book. I expect that most of you do not have a copy of the book, and that's okay. You're not going to really gain much from it because he uses SAS to do all his plots or all the stuff that he's doing. Also, he has some little bit different interpretations than what I have here, and in terms of the focused questions that I ask you. So I don't really think there's much of a benefit at all to having Dallas's book for this if you don't have it. Okay, so what we have here is 48 individuals who had applied for a job with a large firm were interviewed and rated on 15 criteria. I guess why I was interested in this particular data set is because the Department of Statistics, for the first time since 2007, it's been a long time, we're actually hiring for a new faculty member in our department. And I happen to be on the committee, the hiring committee for that, and so we're going to be looking through lots and lots of applications. And of course, when you do that, you need to figure out, well, which ones look good, which ones don't look good, so you can decide who to bring in for an interview. And so that's what motivated me to look at a data set like this, because multivariate methods can be useful for that purpose. Okay, so we have 15 criteria that everyone was rated on. So for example, one's called the form of their letter of application, which is denoted by the variable abbreviation FL. The data set is available on my graded materials webpage. They were ranked or rated based upon their appearance, their academic ability, all the way down to their suitability. Each of the criteria for each of the candidates they were rated on an integer scale from 0 to 10, with 0 being very low, 10 being very high. So ideally, if you were one of these applicants, you want to be as close to 10 as possible. Okay? Again, the data is on my website. That's the actual data file, comma delimited file. So problem number 1 here, 10 points. It says, examine appropriate plots of the data and interpret them in the context of the problem. In your interpretations, make sure to specifically indicate which individuals are good overall applicants. Again, good overall applicants, I have lots of 10s, okay, for their variables. Now, this is kind of an open-ended question here. Some of you might do one set of plots, and other people might do other kinds of plots. But hopefully you don't take advantage of this open-endedness and say, okay, I'm just going to do a scatter plot of keenness to join and suitability and call it good. That obviously is not going to give you a good understanding of the data set if you just did one scatter plot between 2 variables. So what you need to do is figure out, well, what plots, based upon what we've been talking about in this graphic section, would be appropriate for this data set so that you can get the most amount of information out of it. I recommend doing more than one plot. Okay? So let's partially do number 1 so that I can show you what I'm expecting in terms of what to hand in, how to do the R part and how to form your interpretations or how to organize it. What I recommend that you do is you download this file from my website and you just simply type in your answers into this file. Of course, save the file with a different name, that has, let's say, the names of the group members. That helps me identify, whose file is who. But simply, do the R stuff, type in your answer, all inside this document. Okay, so first of all, of course, you're going to need to read in your data. So I'm going to read in my data using, I could use the read.csv function. I use read.table here. And I'll probably want to use the head function on it to make sure that I got the data right. And it looks right if you compare it to the actual data file. And then, probably one appropriate plot to use in this situation would be a stars plot. I have all these applicants. Each star is going to represent a particular applicant. And so I'm going to open up a new graphics window. I don't have to do this, but I want to have it a little bit wider than normal. So that's why I decided to do it. And I'm going to use the stars function. I don't need the first variable that's located in the data set because that is just an applicant number. And so I'm just going to take set1, remove the first column. I'm going to then do a star plot similar to what we've done before. Okay, so now I have this. Here's my star plot. So now what do you turn in then with me? Well, I will be actually at times trying to duplicate exactly what your code did. So I will be copying and pasting code from your Word document into R. And if I have some code that does not work, then you will probably be missing some points on your project. So since I have not actually ever read in my data yet, I'm going to copy this part into my, my Word document. And then the corresponding code that generated my plot, I'm going to copy that as well. I'm going to bring this over to my Word document. I'm going to paste it in there. Also, I'm going to paste it in my plot. Now, when you copy and paste code and output into a Word document, this is what it might look like. Okay, might look like this. This is not good enough to turn in. You need to format it so it looks nice. So, how do you do that? Well, let's see here. You might have to, let's say, put some enters in there. I'm going to move this over a little bit. I'm going to take out that plus sign, bring that up like that. What else? I don't need this little part right there. I'm going to bring this part up, and I'm going to move this over. And then I'm going to change the font so it's a courier font so that everything lines up nicely. So you can see here when I just copy and paste the data set here, you can't tell which variable corresponds to which set of numbers. And so if I use one of these fonts, like a courier font, that has the same width for every single character, you'll notice how things are a lot nicer. And I might need to do a little fix there too. There we go. In essence, what I'm trying to say, maybe I should have said this at the very beginning, the code and the output that you put into your Word document should look just like my code and output that's in my notes. Okay? That's just to make it look nice. I have to look through, I would imagine, probably about 15 or 20 of these. And if everything's not aligned, if it's very difficult for me to read in terms of, I have these plus signs, these continuation symbols that you see here, and if it's just one big mess, it's just very, very difficult for me to grade. Okay? So that's what I'm expecting. Your code and output should look like what's in my notes. Now that I have this in here, it's properly formatted, now I need to interpret it. The star plot shows that, what does it show based upon this data set? Why does it show this to me? Why does it show me maybe that applicant number 44 might be one of the best? Because the stars or the rays of the stars showed this quality. So when you interpret these plots, give me the verbal, give me the interpretation, but also tell me why you came to this conclusion. Because I'm trying to grade you on that you fully understand what these plots represent. So if you only said, the star plot shows that applicant number 44 was the best, and you just left it at that, that will not get full credit. You have to tell me why it shows that number 44 is the best. Is that clear? Okay. So that's what I'm looking for what you to turn in. Now, problem number 2 here on the project involves principal component analysis, and that's the next topic that we will discuss in our course, so I'm not going to go over this part right now. Are there any questions about this project or my expectations with respect to this project?
So we should have all the outputs on the...
All R code, all R output should be in there. So like I said, I will often be trying to duplicate what you did to make sure that you did get it right. It also is very helpful when you don't get something right. I know I can figure out a lot easier why you didn't get it right because you have shown your work. Any other questions? Yeah.
So first question, did you want the code within the question or put it in all? Like the stepwise process or?
Within each question, you should have the code and output together. Okay? Other questions? Okay. Why don't we then continue in the notes? We're on page 46. Okay, so far with these trellis plots, we've looked at situations where we have a, roughly speaking, a variable that we're conditioning on that has a fixed set of levels to it, like shelf, 1, 2, 3, 4. But what happens if you had, let's say, another variable that you want to condition on that's continuous? Well, what you have to do is form what's called a shingle in trellis plots terminology. You need to form a shingle. And basically what the shingle is a way for you to, let's say, condition on a range of the continuous variable. So, for example, with this sodium variable, it's, roughly speaking, it's continuous. And so what I can do is divide up the sodium values into particular, let's say, classes. Like, for example, maybe 0 to 1, 1 to 2, and 2 and above. And then do plots based upon those classes. Okay. So to form a shingle, you need to use a function called equal.count. And I'm going to form the shingle based upon sodium. I'm going to say I want 3 classes formed, 3 groupings formed, where I actually allow for an overlapping of observations, so that observations can be in more than one group at a time. This is kind of useful because we're kind of artificially creating these classes, these groups. And just for demonstration purposes, I say 0.1, which means 10%. So these classes will share 10% of the same observations. I'm going to put that in an object called sodium.group. Let's take a look at it. So it gives me my original data, but it also shows me what my classes are. So the first class starts at 0, goes up to 5. There are 14 members of it. This next class, a little bit less than 5, goes up to 16.33. There are 14 members in it. The last class, notice how it also overlaps the previous one because its minimum value is less than the maximum value of the previous class. There are 15 observations in it. Notice in total, there are 43 different, if you add up this count column, there's 43. But remember, there's 40 observations. This is because of this overlapping. And we have some information about how many observations are in each overlap. Okay. Now, just to verify that indeed that this is basically a character, essentially a character variable now, you can use a function called levels. So if I say levels sodium.group, you see that there are 3 levels to it, where you see the minimum and you see the maximum value for each level. And so let's do a scatter plot again, sugar versus fat. We're now going to condition on sodium.group. I'm going to make one little small change to it from what was in the notes. I'm going to use the layout argument to change it to being a 1-column, 3-row plot. So it's a little bit different. And there's my plot. Again, 3 different scatter plots. And now also you can see, similar to what we had before, you see this little bit of a darker color here for each panel title. We saw that before with the first time with the shelf variable. Well, here you can see the purpose of doing that. This allows you to see what range essentially that third variable, that conditioning variable, corresponds to. So you can see for sodium group, roughly speaking, you go from 0 to almost about the median. And you can see that there's a little bit of overlap here for this middle class between where the darker orange is. You also see some overlap here between the darker orange. And you can see, roughly speaking, that the top panel there corresponds to the highest sodium values. Let's do another example just to help illustrate this better. Suppose I do an overlap of 0.25. You can run this. And now you can see that overlap in terms of those darker oranges a little bit better. Okay. Are there any questions? No, unfortunately, we did not finish this section. I tend to spend more time on the graphics section than maybe perhaps other instructors do. The reason being is because we don't actually have a graphics class at this university. Some departments of statistics actually offer a course on statistical graphics. So that's why I like to spend probably an extra day on it. And I guess we'll just finish it up next time. So if there's no questions, then that's it for today.